Okay. Next point. So we're done with part one for today. Yeah, we're done with this part. Now we need to do formalism and statistical mechanics. This is when the fun starts. So let me tell you about this history. Oh, there we go. Scientists, when it first started, when quantum mechanics first began, people like Maxwell, Boltzmann, and Gibbs tried to apply the formalism of classical mechanics to explain statistical mechanics. That developed a field called classical statistical mechanics. What they found was they could not explain everything. This is nowadays called the Maxwell-Boltzmann or MB statistics. This was very good at explaining things like pressure, temperature, etc. for gases, but could not explain things like black body radiation. Ultraviolet catastrophe, specific heat at low T's. So a new kind of, this implies, a new kind of statistical mechanics must be developed in order to explain those things. And that was called quantum statistical mechanics. And even that could not completely explain every new thing that we were finding. So that was also split into two parts. One was called the Bose-Einstein statistics, and the other was called the Fermi-Dirac statistics. See how complicated it's getting? Now, how do we have these two distinct statistics? Well, quantum statistical mechanics uses two main principles newly developed in quantum mechanics. One is called the Pauli exclusion principle. Okay, what does the word exclusion mean? Excluded. So think about what these two words would mean. Pauli is the name of the guy. No two fermions can be in a single state. Exactly. So it limits, Pauli's exclusion principle limits the number of particles occupying a single state. That's what it means. It just is a limiting thing that we will talk about. And the second one, which is the result of Schrodinger's equation, says there is a finite number of states in any interval E to E plus delta E. You cannot have an infinite amount of states in any interval.